Good day and welcome to our class on sequence divergence. For this class, we want to prove that the sequence minus 1 raised to power n for all n belonging to the set of natural numbers diverges. We want to prove that this sequence diverges. However, before we begin to prove that it diverges, let's consider the terms of the sequence. Consider the terms of the sequence. What are the terms of the sequence? The first term, when n is 1, we have minus 1. The second term, when n is 2, we have 1. The third term, when n is 3, we have minus 1. The fourth term, when n is 4, again we have 1. What does that tell us? Therefore, for even value of n, the term is positive, is plus 1. And for odd value of n, the term is minus 1. Therefore, the term of our sequence is oscillating between plus 1 and minus 1. We are now certain that truly this sequence does not converge. The sequence minus 1 raised to power n does not converge because it does not get closer and closer to a given real number. We now know that definitely the sequence diverges. The sequence diverges. If it is actually diverging, then the next question we need to ask ourselves is, does it diverge to positive infinity or negative infinity? That's another question we need to ask ourselves. Is it diverging to positive infinity or negative infinity? Let's go and look at that. The sequence is not diverging to positive infinity or negative infinity. But we know that it is not converging. Therefore, it is diverging. Now, for us to prove that it diverges, we need to do what? Prove by contradiction. Therefore, we need to prove by contradiction. We want to prove by contradiction. Therefore, we will suppose for contradiction that the sequence converges to L belonging to the set of natural real numbers. We want to assume that the sequence converges to L. What does that mean? That means that there exists a L belonging to the set of natural numbers, the set of real numbers rather, such that An converges to L. We want to show by definition of convergence that this statement, that our sequence An, in this case, our sequence An is what? Is the sequence minus 1 raised to power n, where n belongs to the set of natural numbers. We want to show that this sequence actually does not converge to L. We need to recall the definition of divergence, of convergence. We need to recall the definition of convergence. What is our definition of convergence? It says the sequence An converges to L if for any epsilon greater than 0, there exists a k belonging to the set of natural numbers such that the absolute value of An minus L is less than epsilon for all n greater than or equal to k. Now, let epsilon be equals to 1 over 2. So we want to show that An minus L, the absolute value of An minus L is less than epsilon. We want to show that the absolute value of An minus L is less than epsilon. Remember that our An is oscillating between what? Minus 1 and 1. Therefore, if n is odd, what do we have? An minus L less than epsilon becomes what? Minus 1 minus L less than epsilon. And we have said that we are assuming that our epsilon is 12. Therefore, it implies that minus 1 minus L is less than 1 over 2. The absolute value of that. And as such, by equivalence, we have minus 1 over 2 to be less than the absolute value of minus 1 minus L, and that is less than 1 over. So when we multiply through by minus 1, we have 1 over 2 to be greater than 1 plus L, and that is greater than minus 1 over 2. And if that is the case, what happens next? We can now subtract 1 all through. We have 1 over 2 minus 1 to be greater than 1 plus L minus 1 to be greater than minus 1 over 2 minus 1. And so we have minus 1 over 2 to be greater than L, and that is greater than minus 3 over 2. Therefore, when N is odd, we have that as the range of value of the limit L. On the other hand, do we still have the same range of value for our L when N is even? Let's go and see. If N is even, again, just as we have done there, we have An minus L to be less than epsilon, and this gives us what? 1. Remember, N is even now. N is even, so we are going to have a positive 1. 1 minus L is less than epsilon, and we have assumed our epsilon to be equal to 1 over 2. That implies that 1 minus L is less than 1 over 2. And again, by equivalence, as I said here, we have minus 1 over 2 to be less than 1 minus L, and that is less than what? 1 over 2. When we multiply through by minus 1, as we did to arrive here, when we multiply through by minus 1, what do we have? Multiply this by minus 1, we have 1 over 2 to be greater than L minus 1, and that is greater than minus 1 over 2. We add 1 all through. That gives us 1 over 2 plus 1, greater than L minus 1 plus 1, greater than minus 1 over 2 plus 1. So we have 3 over 2 to be greater than L to be greater than 1 over 2. Again, this gives us the range of value. This gives the range of value for N when N is even. Now, if we look at the range of values, what does it tell us? When our N is odd, if N is odd, our L is negative. As we can see, in the range of values of our L, beginning from minus 1 over 2 to what? Minus 3 over 2. Minus 1 over 2 greater than L greater than minus 3 over 2. And if N is even, again, as we can see here, our L is positive. L is positive. So what does that mean? This is not possible. And if this is not possible, it means that by contradiction, we have been able to prove that the sequence actually does not converge. This is not possible. As such, this is a contradiction. This is a contradiction. Therefore, the sequence does not converge. The sequence does not converge to a real number L. And that implies that the sequence minus 1 raised to power n for all n belonging to the set of natural numbers diverges. And that is what we have been able to prove. If you have benefited anything from this video, or if you think this video is useful, then you can give this video a thumbs up, like it, and share with your other colleagues so they can benefit from our class on real analysis. Thank you. God bless you. I see you in the next video.